Have you ever wondered what the universe is made of? Well, in this edition of The World Transformed, we're joined by our good friend Jim Elvidge, who talks about his new book, Digital Consciousness. And in part one of our three-part interview with Jim, we get into the question of whether the universe itself is digital. Do we live in a universe made of stuff or a universe made of numbers? Jim's going to step us through the science, and you might be surprised by what science has to tell us about that question. Stay tuned.
We live to see it, friends, and welcome to The World Transformed. My name is Phil Bowermaster, and I'm pleased to welcome you to part one of our three-part interview with our very special guest, Jim Elvidge. Jim holds a master's degree in electrical engineering from Cornell University. He's applied his training in the high-tech world as a leader in technology and enterprise management, including many years in executive roles for various companies, entrepreneurial ventures, and leadership consulting. Outside the world of high-tech, Jim has years of experience as a science researcher keeping pace with the latest developments in such fields as quantum physics, cosmology, artificial intelligence, nanotechnology, and metaphysical anomalies. This unique knowledge base provided the foundation for his 2008 book, The Universe Solved, which presented evidence that our reality may be under programmed control. His research and theory has continued beyond the simulation hypothesis and incorporated powerful ideas around consciousness, cultural synchronicities, quantum anomalies, and a true scientific foundation for digital consciousness theory, which is what we're going to be talking with him about tonight. I should also add that Jim is a good friend of this show. He's a co-author of our book, Visions for a World Transformed, and we're going to be talking about his new book tonight, Digital Consciousness. Jim, welcome to The World Transformed.
Oh, thank you very much, Phil. It was great to be on with you again on The World Transformed. We go back a long way. We've had quite a few shows together, so it's always great to talk to you.
I think, the first time we talked, it was before Universe Solved was quite out yet, right? So we've been talking about this stuff for a while. It's exciting to see how these things have come.
Almost 10 years.
Yeah, it goes back a ways. So here's the first question I think that everyone's going to want to know the answer to. Okay, so why did the guy who already solved the universe feel like he had to write another book, right? What else is there to do, right?
Yeah, great question. I mean, to be honest, the titles of the books aren't exactly representative of the book. The Universe Solved doesn't really solve everything. It's a great title, though. And it was, the first book was basically, I think, kind of novel at the time because there were some other people thinking about the same kinds of things, but it was more about the evidence supporting the idea that we are living in a digital simulation of some sort. We could talk about what that word means in a bit. And it didn't go much beyond that in terms of, how does it work, what's behind it, things like that. I was pretty much agnostic about all those things. But now 10 years later, a lot of people have kind of jumped on that simulation bandwagon, scientists and, media people, Elon Musk, others. You read articles about this kind of thing all the time. And the thinking has actually gone a little bit further, a little bit deeper. The basic ideas are the same. However, in this book, what I've done is really tried to make more of a scientific argument for it. And that the purpose of that is there are a lot of people on the fence about these kinds of things, and I'd like to give them something to really think about and to think, okay, it makes sense when you look at it from a scientific methodology standpoint. It may be a little bit more impactful that way. In addition, I created a visual model of how it all works, and so every one of the anomalies we talk about, any one of the different areas that this explains can be shown in a visual model in the book, so it makes it a lot easier for people to understand. And in addition, there's just tons more evidence and things to think about. The final thing I think I brought into this book, which was missing in the first one, is a real connection to ancient religions, Eastern religions and spirituality, ideas like that. And it's important because these things don't come out of nowhere. They're not just made up. And the fact that they're very much aligned with what we'd be talking about tonight is surprising in a way, but it's also more impactful, I think, as evidence for the truth of this kind of theory.
For sure. Well, I enjoyed the book immensely, and I would just, in response to what you said about the process of putting it together, I noticed that there's a heavy scientific component, as there was in the first book, as there was in The Universe Solved, setting up kind of the science of it. A lot of physics in there. And I was reading your book at the same time, coincidentally. I happened to be reading Our Mathematical Universe by Max Tegmark. So it's interesting. There's some kind of dialogue between those two, and we'll get into that a little bit down the road. I know there's some distinct differences as well. I realize that there are, but some interesting common threads there. And some other books I've been reading about physics lately, you basically lay it out, right? You tell about what's going on in science, and then what it really implies. And then what it really implies, we end up in this very different kind of book about spirituality and about the meaning of life, and also about things like UFOs and stuff like that. So it's tremendously entertaining, but at the same time really covering an awful lot of ground, isn't it?
Yeah, it definitely is. And I read that book by Max Tegmark also. I like Max Tegmark. He was one of the guys that did some, great thinking about parallel realities and parallel universes, sort of different dimensions of that idea. So he was one who made the point that we've never measured anything to an accuracy below, I think, 10 to the minus 16th meters or that many orders of magnitude. So, when people argue that the world is continuous versus digital, they really can't make that argument because we haven't measured anything down below that level. There's really no evidence at all for a continuous reality, and he's also, I think, in support of that idea. A lot of scientists.
Awesome.
Yep.
You have just anticipated my first actual substantive question, because what I thought we would do here is I wanted to set out this first show. I thought we'd talk a little bit about the kind of the scientific case for whether we live in a simulation or not. And my first question, I was just looking at it here, is the universe continuous or discrete? And here you are answering the question already before I even asked it. So what does that tell you, huh? Right there. Something weird going on.
Great minds.
Yes.
Okay, so shall I go ahead with that?
Yes, I'm sorry. I'm sorry to interrupt. I was just so excited. It's like, hey, he's answering the question before I even get a chance to ask it. So we live in a discrete universe. Is that? I mean, that's what the evidence seems to indicate.
Yeah, and it may sound odd, but when you think about it, why not? The ancient Greeks thought we lived in a discrete universe. They coined the term atoms. Everything was discrete from an atomic standpoint. And there were philosophers, I think Plato believed in it. So did Zeno. You've heard of Zeno's paradox, even thinking about time being discrete. So it's not a new concept at all. But, as we look at things macroscopically, it doesn't look discrete. You see flowing water, you see, things that have texture and so forth, and it feels continuous. But then the question is, how far down do you need to go before you determine that things are discrete at all? And, quantum mechanics certainly, changed the way people thought about that, because the idea of energy coming in, units of quanta related to, Planck units and things like that, that was new. That's only 100 years old. So there was some real evidence that deep down things are quantized, and it doesn't necessarily mean that they are. I mean, if you look at an analogy, I've often used this analogy like a rock dropping in water. You see discrete waves coming out, but those waves underneath, what's functioning in those waves is a continuous flow of water. But that water is made of atoms, which are discrete units, but those atoms may be fields, created by, the electromagnetic forces and so forth, and those could be continuous. But deeper down, if those fields are based on particles, say strings, or, even subatomic particles down, when you talk about that, then that could be discrete. And you keep on going, at some point, there's an answer there. And it's my belief that when you go deep enough, there really isn't any substance, that it's really just information. And that would basically say it's a digital discrete world based on information. On the side of whether it's continuous or not, there's no data. There's nothing that supports that other than the fact that at a macroscopic level it looks like that. But then again, the Earth looks flat when you're walking around too. It doesn't look round until you're in outer space. So, our perception of things depends on the scale that we're looking at, and to make some assertion about the Earth being about reality being continuous based on a macroscopic view of it is false. You can't do that. So then you ask the question, okay, well, there's no evidence that the reality is continuous. Is there evidence that it's digital? And I mentioned the one thing, the quanta of energy. Things in quantum mechanics appear to move and be in discrete quanta of these units. That's one thing, but you could also look at the lack of evidence for things that are moving at a smaller level than that. So, for example, if we had continuous reality, that means that we have essentially infinite resolution of our space and our time. If we had infinite resolution, that means that there's something in there, there's some structure to it at an infinitely small level. Well, when there's something at an infinitely small level, then the inverse of that is infinitely large. Things that move have an inverse, an inverse to a wavelength is a frequency. So the frequency, if we had, a very infinitely resolvable reality, then we should see evidence of frequencies above 1 divided by the Planck length, for example. But we don't. Hawking radiation dies out at the Planck length, at 1 over the Planck length. So that's just one example of something that shows that there isn't something that relates to a resolution, below the Planck level. That kind of implies there's something discrete there.
Right.
One other example.
Oh, go ahead.
Sorry, Phil. Just one other example I'll throw out from the field of physics is the idea of spin values on particles. Spin values are always discrete. A particle either has, an integral unit, 1, 2, or -1, something like that, or it has units of a half or minus a half, or 3 halves, something like that. There's never anything in between. So when there's a nuclear interaction, the spins of particles may flip from +1/2 to -1/2, but they don't go through all of the other values to get down to the -1/2. They go immediately, instantly from +1/2 to -1/2. And nothing in a continuous world works that way. So that kind of implies that spin values are discrete, and if spin values are discrete, then the underlying reality is probably discrete.
Absolutely. Well, I was just going to say, to sum it up for people who maybe aren't familiar with all of the physics, what we're talking about here, the basic idea is, I think most people are familiar with the idea that matter is discrete. Ultimately, you can only break it down so far, right? You can take any object in front of you, if you keep cutting it in half, eventually you get down to something called an atom, which it can be broken down into smaller parts. But the thing itself, ultimately you hit a place where it's just a fundamental chunk, whatever that is, right? Whatever that is, there's something at the bottom, right? Beyond which you can go no smaller. And ultimately, what physics is telling us is that's true about everything, right? It's not just physical stuff, but it's true about space and time itself, right? That the universe itself seems to be ultimately discrete. Ultimately, it's made up of small bits of something, and the analogy of bits is to a digital system, right? That it's like pixels, finally, right? Is kind of what you get down to. That we live in a kind of a pixelated universe.
Yeah, exactly. It's pixelated in time and in space. And, I want to just kind of caution the listeners, the people who will be listening to the podcast, that the idea of the world being digital doesn't take anything away from its beauty or what you can do in it. It doesn't make it mechanical or reductionist or automated or anything like that. It doesn't take away free will. All it does is it means that the structure that it's based on is something different than what we might have thought about before. So sometimes people say, oh, that just sounds so cold and calculating because we use words like digital or words like simulation. Unfortunately, we don't really have a good lexicon for this philosophy, for digital philosophy. We use words that are already kind of loaded in people's minds. Words like digital, when I hear that, I think about, bits in a computer, and it feels very cold and calculating. But movies move people, and movies are digital now, and they're, discretely shown on a screen. When we go to see a movie, we might see 48 frames a second or something like that, but it looks very continuous. But it's really just discrete information coming into our senses. So it's not a cold and calculating idea. In fact, it's, it has nothing to do with things like, beauty or flexibility or creativity or free will.
Yeah, it's the same place either way, right? Whether it's continuous or discrete at bottom. Absolutely. So let's talk about this. Why are only simulation arguments consistent with technological evolution? You spend some time on that in the book, and I think that's really interesting. Why is it that the simulation arguments comport better with that than other ways of looking at things?
Well, I think a lot of this probably goes back to Nick Bostrom's idea and his simulation argument. The idea is that as we evolve our technology, and it's been for the last 40 years kind of advancing at an exponential rate. Moore's law says every 18 months or so the density of transistors doubles, the speed of processing systems double, and things like that. So since we can now create some simulations, you look at movies that are completely fabricated, computer generated, or some of the virtual reality experiences that you can have even on like a Sony PlayStation. They seem very real. They look real to you. The sounds are real. You can look around 360. And so even though you're in a simulation because you remember when you put the headset on, we're also experimenting with things like uploading memories, archiving memories, implanting new memories. They've shown the ability to implant memories, believe it or not, in, I think, worms or mice, teaching them how to get out of a maze and things like that. So we're experimenting with that, and it's not hard to imagine a future, whether it's 10 years out or 20 or 50, a future where you're able to suppress your awareness of the reality that you're in for some short period of time, load up a simulation, whether it's through an implant, a mind probe, some nanobots, or clumsy haptic devices that you wear. It's not hard to imagine this kind of thing being possible to the point where you can't tell the difference between that and a real reality, and you can't even remember that there was a difference. So if that's going to happen at some point, as the argument goes, how do we know that it hasn't happened already? And Nick Bostrom's argument is, once we get to that point, that's the post-human stage in his lexicon, then we'll create millions of these simulations. So the odds that we're living prior to it is very low. So either we don't get there at all by choice or by the fact that humanity will get destroyed, will destroy our own civilization before we get there, or we do get there, and if we do get there, then we're most likely living in a simulation now. So the whole technology argument also lends support to this, but it's a different argument than what I have, and it gets kind of confusing because when you talk about simulations within this reality, I believe that this reality itself is a simulation of sorts. So we're nesting our simulations, really.
Right. And of course the question comes up, and we'll get to this probably in part 3 of this discussion, as to whether we might be embedded in one of those, whether there are layers, and what the chances are that we're buried in one of those. But we'll come back to that, because I want to just kind of stick with laying the groundwork for why it looks like, all things being equal, we live in a simulation, why that seems to be the best explanation. And another piece of that you talk about in the book is the fact that we live in this very fine-tuned universe. We live in a universe where if you changed any variable to a very distant decimal point at the beginning of the universe, we're not here. right? Planets aren't here, matter isn't here, or life couldn't exist. There's so many different ways it could have gone terribly wrong. And even when you get down to this planet, it's situated in exactly the right place. You move it a little closer to the sun, we wouldn't be here. A little farther out, we wouldn't be here. There's this whole amazing set of coincidences that all had to fall in place in order for humanity to exist. So this is one of the interesting challenges that scientists have to try to overcome. You end up with this anthropic principle, and there's a strong version of it, and there's a weak version of it, and there's this whole question of why did all these amazing coincidences happen? How did we get here? And you make the case that simulation provides a better explanation for that fine-tuning of the universe than anything else that's out there. Can you give us a quick recap of why that is?
Sure. So just as an analogy, if I were going to design on a computer a game that had a physics engine in it, it would all have to make sense. It would all have to fit. The people in the game who are discovering how fast things drop when you drop a rock in your virtual reality, and then kind of putting all this stuff together, it would have to be consistent with how that game works. So, there's the anthropic argument is a crazy one. It's basically saying, well, of course, everything seems finely tuned for life and for matter and energy and so forth. And by the way, it's almost hard to use that word because it's so incredibly perfect. Universal constants and vacuum energy cancel each other out to one part in one followed by 115 zeros. I mean,
it's a ridiculous coincidence that we're here, right? It's absurd.
Exactly. Yeah. It's absurd. So the only argument could be, well, of course we're here because this is the only universe that would have us. It's designed this way. But that kind of implies that there's another, 10 to the 115th out there. Well, actually, that's just one attribute. You have to multiply all these attributes together. Deviations in the ratio of proton to electron, all these kinds of things have to be so perfect that to have enough universes out there where we happen to be in the right one, it's an astronomically huge number. So the argument is, well, there must be, many universes. There must be zillions and zillions of them, and we just happen to be in the one where everything just lined up. And I don't know. To me, that doesn't pass the sniff test. And more scientifically, the concept of Occam's razor. I forget, William Occam, I think, came up with that the simplest explanation is most likely to be true. Well, what's simpler? That there are zillions of universes created through some strange mechanism, and that we happen to be in the one that's absolutely perfect, or it was just designed that way. The latter just seems to be so much simpler. Now, it doesn't mean that there's an entity out there like, an alien hacker or an AI that created our reality for us and is looking over us like the architect in the Matrix. It doesn't necessarily mean that. It could be that the construct of reality didn't work well at first, and it's driven by some, rule of continuous improvement where it keeps on modifying itself until things work. And eventually over time, it's modified itself corrected to the point where it is very finely tuned for the experiences that we need. Stephen Hawking even kind of explores something like that. I forget what he called it. Kind of a reach-back mechanism where the universe could, knowing that it has to get to a finely tuned state, it could reach back and change laws in the past through some quantum, anomalies. But even that one is, that seems to be a little bit of a stretch. It's just simpler to say, however it got designed, it's designed for us to exist, and that just makes sense.
There you go. So if it's a simulation, it's by definition in some way designed, right? There's some design principle that has been applied to get us here, and you think about if you found, I know there's the old, and I don't know who came up with that a long time ago, back in the Middle Ages or during the Enlightenment. Somebody had the metaphor of the watch, right? A watch implies a watchmaker,
Mm-hmm.
and this was kind of the argument for the creation of God, or that God created the universe. But just the idea, if you're walking in a desert and you found an iPhone, right? And you thought, wow, imagine the amazing coincidences that would have to occur, to turn the silicon in this desert into this object, right? It's ridiculous, right? It makes a lot more sense to say there was some process, there was some design that was implemented that enabled this amazing thing to come into being. It makes an awful lot of sense. Well, another idea that comes up in the book, and you alluded to it earlier, is this notion that matter is composed mostly of information. So we were talking before about things being discrete versus continuous, and discrete implies that you can break things down into pieces. But as you said earlier, maybe there are no pieces at the bottom, right? That ultimately it's just information. So what is trending? What's happening in science that's leading scientists to believe that maybe matter is just information, maybe everything is just information?
Yeah, that's a fascinating one to me. And I kind of use the idea of extrapolating a trend. So we use extrapolation all the time. If we know that the population is increasing at a certain level, then we can predict, 10 years out, it's going to be at a certain level for various countries. They're predicting that the population of India will surpass the population of China in 5 years because they're extrapolating out the rate of population increase, as an example. And as far as I know, nobody's thought too much about the idea of extrapolating what's really going on with the perceived definition of what matter is, but it's fascinating. If you turn the clock back a couple hundred years, even I'd say late 1800s, the prevailing view of matter was still what the ancient Greeks had, which is, we have these little billiard balls of atoms, which are hard, solid things,
right?
And everything is composed of those. So,
it's like a universe made of ball bearings or Lego blocks or something like
exactly.
that. Right?
Yeah, and they all respond according to some rules, and we just haven't worked out all the rules yet. But we're working on that.
Yeah.
And so, the ultimate density of matter, then, if you were to put a bunch of billiard balls together, there's a little bit of space between them, and so if you define the constituents of those billiard balls, I use the word stuff because we don't have another definition, but something
good word,
physical and real. It's stuff. There's a little bit of empty space, and if you jammed a bunch of billiard balls together, the ratio of stuff to empty space is like 70-some%, the way it works out.
Right.
Well, in the early 1900s, Ernest Rutherford and some other scientists did these experiments where they found that, oh my gosh, the atom is really mostly empty space. It's this electron cloud with this tiny little dense nucleus. So most of the atom is actually empty stuff. In fact, for every piece of stuff, there's 1 followed by 15 zeros worth of empty space.
Right.
In that theory. So the ratio of empty space or stuff to empty space is 1 to the minus 1 times 10 to the minus 15. Okay, so that was 1920s, roughly 1910, 1920s. Then in the 1960s, quark theory came about, and they found that protons and neutrons, these things that we thought were the indivisible nucleus of an atom, they're actually mostly empty space, and they consist of quarks. And so now, if you do the math, the ratio of empty space to stuff is 10 to the 30th. Well, the string theorists came along in the 90s and said, well, even every particle, even quarks, are just made of strings, and the strings have a width of a Planck length, which is somewhere around 10 to the minus 35 meters. So those, even quarks, are mostly empty space. Now, this is where it gets interesting to me because, according to string theory, every single subatomic particle only differs from the other subatomic particle, and all the behaviors that it has and all its ways of interaction, it only differs because of the vibration of that string. Is vibrating at a different frequency. Well, if your string is vibrating at a different frequency and that's what defines a different piece of matter, what do you need the stuff for? You just need the number, the frequency. You can derive how the matter behaves and how it responds, and you can derive all the rest of the rules just by that one number. So with string theory, we're down to, a tenuousness of space, of matter in space of 1 times 10 to the minus 52, even within atoms. And the trend, if you extrapolate this trend out, we keep on getting toward less and less stuff. So at some point, the direction we're going is there's going to be a recognition that there is no stuff. And a lot of physicists have already come to that conclusion, that deep down, matter is just information. I think it was John Wheeler, perhaps, that said it from bit.
It from bit, yeah.
Yeah, so I'm certainly not alone here. I'm not the one that came up with this idea. I think what my contribution here might be in this area is this idea of the extrapolation of how tenuous matter is, and I plot it out in the book and show how crazy it is and where we're trending. We're trending toward the realization that there is no stuff, that it's really just information.
The harder you look, the deeper you go, the better you get at looking for it, the more apparent it becomes. There's nothing there, right? It's
exactly.
It's an amazing thing. And Max Tegmark talks about this in his book as well, and I think it's really interesting when he talks about his mathematical version of the multiverse, but he's just talking about kind of the idea in his view that the whole universe is a mathematical construct, similar to the idea of being a digital simulation in some ways. But he works through that same thing, and he says, finally you get to the bottom, and all you've got are these forces, which are really these mathematical relationships. You've just got these numbers working against each other. That's finally what you find when you get to the bottom. There's nothing else there.
Exactly. And Phil, when you think about it, I mean, this is where it gets into consciousness too. We think there's stuff because we feel it. When we knock on a door, we feel something hard, but there is no molecules in our knuckles that are touching the molecules in the door. All it is the force, the electromagnetic force between the molecules in the knuckles and the molecules in the door that are impacting us and giving our nerves the sensation that there's something there. So we don't ever really feel stuff anyway. And if you think about what we perceive, how we collect information, it's all subjective. And it's all based on our consciousness, collecting information through our various sensory, organs that, give us some sensation of stuff. But there really isn't anything.
There's nothing. Finally, there's nothing there. Sensations ultimately are going to be numbers too, right? It's ultimately going to be that's information too. Finally.
Yeah, and you know what? There are so many amazing physicists. I mean, the people who, Nobel laureates, people who really thought out of the box. They struggled with a lot of the same ideas. For example, Max Planck. He said, I regard consciousness as fundamental. I regard matter as derivative from consciousness. Max Planck said that. Albert Einstein said, reality is merely an illusion, albeit a very persistent one. and Niels Bohr said, everything we call real is made of things that cannot be regarded as real. I mean, these guys who were, experimental physicists and this stuff, they were coming to the same idea. Really, they just couldn't, I don't think they could put it together. I think, one of the advantages that I've got and other people have here is, two. One is, media has made this more acceptable. Movies like The Matrix got people thinking about it. Computers, living in a computer world, and you realize what you can do with a computer has gotten us thinking about how it seems to model reality very well. So we do have that advantage. And the other advantage kind of a non-scientist has is scientist is a person who has a very deep set of knowledge about a specific thing. But to be able to kind of connect dots and see bigger pictures, maybe not so much. I mean, some of them are really good at that, but others get so wrapped up in their niche that it's hard to see the bigger picture. And I think when you kind of step back and look at, what explains some of the things that are going on in the world, what explains this and that, it actually all kind of falls together like a jigsaw puzzle, if you take the simulation model.
One of the interesting ideas that jumped out at me as I was reading this, and I think we actually talked about this a little bit last time you were on the show, is this notion if ultimately it is all information, if it is just math down there at some level, then we're actually finding examples of where math equations seem to be driving reality itself. Can you talk a little bit about that?
Sure, yeah, that's a good one. Even if we did talk about it before, it's a good thing to come back to. There are experiments that show that equations appear to create reality. And the one example that I'll use is Maxwell's equations. So you remember back in high school math days, if you took a square root of something, what's the square root of 9? It's 3, but it's also negative 3. But in some cases, you throw out the negative 3. So, for example, if you were saying, I have a square that is 9 square feet in area, how long is the side? Well, the solution to that is to take the square root of 9, and you get two solutions. You either get 3 or minus 3. But it doesn't make sense to say the length of the side of a square is minus 3 meters or whatever. So you throw that number out. And the same thing happens when you have equations where you're taking the square root of powers of variables and things like that. You get imaginary numbers, these numbers that are shifted by 90 degrees in the imaginary space, or you get some negative numbers like the square root of -1 that doesn't make sense. So you throw those solutions out. However, in some in some cases, those things that you're throwing out, if you don't throw them out and then you apply the further equation to it that has things like artifacts or what's the word I'm looking for, harmonics, then those harmonics shouldn't exist if they're not coming from a real thing. So, for example, I'm throwing out minus 3 because it doesn't make sense in a real world, but that minus 3 is generating harmonics in the equation that are observable in the real world. So it doesn't follow. You see what I'm saying? It's almost like the equations are creating reality in that case as opposed to the other way around. Another example was physicist James Gates discovered what looked like error correction codes in the laws of string theory. Now, string theory is not a proven theory, so to me that's not really evidence that there's it's another example of equations creating reality. But it is kind of interesting that in the best new theory we have in the scientific world, we're seeing error correction codes come out of what appear to be the laws of nature. That doesn't make a whole lot of sense unless there's a big digital system going on.
It's pretty amazing when you take just those three we've talked about here in a little bit of depth. The idea that ultimately the universe seems to be discrete. It seems to be digital, right? It seems to be pixelated. You go looking for the actual stuff in the world and you can't find it. The deeper you look, the more you find that there's just forces, and those forces come down to these information relationships. And the idea that ultimately, the more we learn about how the physical world works, it seems that actual mathematical relationships, equations, are driving the whole thing. Mm-hmm. That right there is a pretty good prima facie case, right? I mean,
it is. It is.
Yeah, we live in a simulation. I mean, it's like what else could possibly account for those three things, right?
Yeah, and the interesting thing, Phil, is like everybody will take one of those things and they'll come up with all these ideas that could possibly explain that thing. Well, what if physics? If we bend physics a little bit here, but for each one of those bending of physics, they don't line up on all of those different ideas. So try to bend physics to explain beta decay being purely probabilistic. Try to bend physics to explain these negative frequency solutions that I talked about. Try to bend physics to explain some of these other things. And you can't come up with a theory that explains them all. The only thing that explains them all is a simulation theory.
Right. And in fact, in the book you talk about, even at this introductory stage, you talk about some just real basic stuff that this accounts for that's pretty hard to account for elsewhere. For example, randomness in physical processes, right? That's something that you can get in a digital model of reality that it's pretty hard to come by elsewhere.
Yeah, exactly. So I mentioned like beta decay. A radioactive atom is going to decay according to some rule, like it'll decay with a 50% probability over the next day, as an example. That's sort of how it works. It doesn't mean it's going to decay an hour from now or a minute from now or a day from now. It might not even decay for 100 years, but it always has that probability of decaying. And Einstein believed, and there were some other physicists that believed there had to be something underlying this that explains that probability. There had to be hidden variables that would say, okay, well, there's something going on here, and as soon as this, the state changes, boom, the thing decays. But Bell and Leggett and others over the last few decades, and the experimental physicists like Anton Zeilinger, they have proven that there are no hidden variables in quantum mechanics, and that there's like this pure idea of a probability function. Well, there's nothing that makes sense, in a continuous reality for that, But I can program a probability function simply in a heartbeat. It's very, very easy to do in a computational model.
So ultimately, when you start accounting for kind of why we're here, when you start answering questions better than other models are able to, and you start providing answers to some of these things that maybe people haven't even thought about, there's a good question to be asked there, why is the speed of light what it is, right? In a digital model, it makes perfect sense. It's one of the parameters you set for the program you're running.
Right. Yeah, and think about the rate that it takes for something to move across a screen on a computer screen, even a super high resolution screen. There's some limit to how fast it can go from one side of the screen to the other, and that limit is based on the physics of how it's built and so forth. So having a speed of light, having a limit there, it makes sense in a simulated world, but it doesn't make sense in a non-simulated world.
And then ultimately, go ahead.
Yeah, go ahead.
Yeah, I was going to say, ultimately, you come to the biggest questions of all. For example, the question of a prime mover, right? What started the whole thing? This is something that theology deals with, physics deals with, philosophy deals with, and a digital model reality gives you an answer to it, doesn't it?
Yeah, it does. And I want to just kind of do a quick shout out to, there are a lot of other people who have thought through these things. Brian Whitworth is one. He's a science researcher from New Zealand or Australia, I forget which. But anyway, he also noticed a lot of these similarities of information systems to reality, and the idea of a prime mover is simple. When you reboot a phone or a laptop or anything like that, that's a prime mover. You're starting it all over. You're setting the thing in motion. When you start up a new program, it creates the substrate for it, and then creates the variables, and it creates the characters and everything that you would need. So there is no philosophical problem with a prime mover in a simulation argument. So that's another area where this explains things that were previously considered unexplainable.
Right. Well, once you hear the word prime mover, once I hear it, and I think once a lot of our listeners hear that, you hear prime mover, and you're going to start thinking, oh, you're talking absolute ultimate questions of reality, right? The question of God comes up at that point, and so that's where I'm gonna wrap this part of our discussion up, and we're gonna pick this up in part 2, which I'm calling God, the Universe, and Everything. And we're gonna see where the digital model of reality takes us in terms of kind of answering some of those bigger questions, because it's all there in your book.
Sounds great.
All right. Well, Jim, great having you with us. I can't wait till we get to part 2 of this discussion.
Yeah, thanks, Phil. I'm looking forward to it.
Looking forward to it as well. And thank you all for being with us. We will be back in part 2 with our discussion with Jim Elvidge. And until next time, live to see it.